Huh? Okay.
You got a 10?
No, I don't. Let me mute you. Where's the mute? Mute everyone. Oh, participants. There we go. Mute all. There you go. You all have been muted now. Okay. Objective, be able to see if an observed distribution fits an expected distribution. Do our observed frequency counts of the categorical variable fit a particular distribution? Examples. Okay, M&Ms. We're going to do the M&Ms example. Example, M&Ms claims its package of milk chocolate M&Ms should contain 24% blue, 14% brown, okay, 16% green, 20% orange, 13% red. They used to not have red because they gave you cancer, but then they brought them back. And then 13% yellow. Do the counts from our bag fit the distribution model? Okay, so this is what they're claiming. They're claiming that this is the proportion of colors in the M&M's bag, and we want to get a sample of that and say, you know, is this a sample? Now, normally, if we were meeting together, we would do this, and we'd actually in class, and we would actually have real M&Ms, you know, and we'd be eating M&Ms at this point. So if you want to go grab yourself a bag of M&Ms tonight, be my guest. Okay. But do the counts from our bag fit the distribution model, or are they off? Okay, O represents the observed frequency from our sample. E represents the expected frequency. Okay, assuming that our distribution claim is true. Okay, K represents the number of categories. So in this case, how many categories are there? That's the colors. So it'll be 1, 2, 3, 4, 5, 6 different categories or 6 colors. Okay, and what's the statistic? The statistic is the chi-squared. So chi-squared is the difference between the observed and the expected. Does the observed equal the expected? Okay, and chi-squared is a measure of does what I'm observing in real life in these categories match the expected. Now we've done where we had one observation, maybe that was mu or population mean, or we did two observations, you know, the difference between two parameters. But now we're doing multiple parameters. Here we've got 6 parameters. We want to see how does that distribution of 6 line up to the distribution of the observed, you know, our statistic. So this would be our statistic, would be the observed, and then the expected would be, right, would be our parameter. Okay, we're just going to use those to get our chi-square, which is our statistic. It's going to be the difference between what we think we should have and what we actually do have. Okay, the chi-squared test statistic is chi-squared. It's the observed minus the expected, comma, parentheses squared, and then over the expected. It's a ratio of those. And this sigma is just sum. We're going to sum all of those up for however many categories we have. Okay, for K categories. Okay, so K is equal to 1, or N is equal to 1 to K. Here, we're going to sum them all up, okay, for however many categories we have. Okay, chi-square test statistic measures how far each observation is from our expected frequency. Chi-squared is always positive. Why is it always positive? Because we're going to square the difference. And when we square something, we always end up with something that's positive. So we're going to square differences here, and then we're going to add them. And so it's always positive or 0. The larger the number, the farther away we are from what we expect. But how far is too far? Okay, how far is too far? So the chi-square distribution looks like this. Okay, chi-square distribution for a certain number of degrees of frequency. And we want to know, and we're always looking at our right tail. It's the right tail here. And we always want to look at our right tail. And that right tail is going to tell me, okay, is this close to what we expected? Or is it really far? Because if this tail is really small, then it's going to be really far from what we expected, and eventually it's going to be less than 5%. That area will be less than 5%, and so we would say, no, it's too far from what we expected, and we're gonna toss out the null hypothesis. Okay, so it's just another distribution that we're going to be working with. Okay. We're going to do one of these by hand. We're going to calculate x squared or chi-squared by hand one time, and then we're just going to let StatCrunch or the calculator do it from here on out. Okay, the chi-square distribution is skewed right. Okay, skewed right. It's always greater than 0, and it depends on the degrees of freedom, which is the number of categories minus 1. Okay, number of categories minus 1. Okay. Okay, let's go back to our example with the M&Ms, making me hungry for M&Ms. Okay, we call it a chi-square goodness of fit test. Okay, goodness of fit test. There are two different chi-square tests. We're going to talk about both of them today. This is the goodness of fit test. How good is the fit to what we expected? Okay. Okay, so the probability of blue, right? The proportion of blue M&Ms was 0.24. The proportion of green, this is what we expect, right? This is our null hypothesis, right? And that's what we expect, right? This is what we expect to be true. Okay. The green would be 16%, the red would be 13%, brown would be 14%, orange would be 20%, and yellow would be 13%. Okay, what is the alternative? The alternative is that only one of these has to be false. Okay, I could have 5 out of 6 of them be true, but if one is false, then I have to throw out my null. Okay, only one has to be false. What's the name of the test? It's the chi-square goodness of fit test. Now on the calculator, it looks like this. Chi squared, chi is a Greek letter X, chi squared goodness of fit test, GOF. Okay, this is what it looks like on the calculator. Chi squared goodness of fit. Goodness of fit. Okay. Number 3, check the requirements. Is it independent? Sure. Is it randomly selected? Sure. Is it large enough? Okay. Is there at least 5 for each category? Okay. Is there at least 5 for each category? Well, it depends on the sample size. Okay. But we're going to assume that our sample size is large enough to get 5 M&Ms for each category. Okay. It just says, we're going to do the calculations first. Okay, we're gonna look at the calculations that we get in step 4. Okay, and we'll come back to this at least 5, and we're going to see that we have at least enough M&Ms to satisfy this. Okay, finding the expected counts. How are we going to get the expected counts? Well, we want to know, out of 200 M&Ms, what is my expected amount of blue? Well, that's just N times P, right? So N times P is going to be my expected amount. Think of it like X, right? When we took 24% of N, right? 24% of n, we got x. That was the amount of successes. That's what we want here, is the amount of successes, okay, which is 48. If you multiply 200 M&Ms, we're just going to let 200 be our sample size. Okay, so we're gonna dump out a bag of 200 M&Ms, and then we would just count. We would count out how many and what is our expected amount based on what the manufacturer tells us. Well, suppose our bag has 200 M&Ms, then the counts are going to be just the parameters, the population proportions times the number of items in the bag. That is what we expect to happen. Okay, so what are these counts, right? What is the expected amount here? Well, the expected amount for blue was 200 times 0.24, which is 48. The expected amount for green was 200 times 0.16, which is 32. The expected amount for red is 200 times 0.13, or 26. The expected amount for brown is 200 times 0.14, which is 28. The expected amount for orange is 200 times 0.20, which is 40. And the expected amount for yellow is 200 times 0.13, which is, again, 26. Okay, this is the number of M&Ms that I should expect for each category in a bag of 200. Okay, so this guy here. This is the expected counts. Expected counts. Okay. Okay, on the next page, we have those expected counts in a table already for us. Isn't that nice? Okay, here was the expected counts that we just calculated. We just calculated these expected counts. Okay. Okay, so when we dump out our bag of M&Ms, this is from our bag of M&Ms. Okay, we ended up with different observations than what we expected, right? Because this is real life. Real life is messy. And so for blue, we got 55. For brown, we got 20. For green, it was 35. For orange, it was 49. For red, it was 18. And for yellow, it was 23. Okay, so in a bag of 200, those were what was observed. So we want to calculate chi-squared based on the differences between the observed and the expected. So here's how this works. We're going to do observed minus expected, right? Observed minus expected squared divided by expected. So observed minus expected all over expected, or sorry, that's squared. And then I want to add all these up. So let's just keep going for each. So this was for blue. Now we want to do this for brown. This is 20 minus 28 squared over 28 plus 35 minus 32 all over 32 squared plus, move this over a little bit, plus 49 minus 40 squared over 40 plus 18 minus 26 over 26, that's squared, plus 23 minus 26 squared over 26. Okay. Okay, if I were to plug this into a calculator, I would get, for the first one, I would get 1.021 plus the second one here, if I square this and divide by 28, I get 2.286 plus this would be 0.281, okay, plus 2.025 plus 2.462 plus 0.346. Okay, now if I added all of these together, I would get 8.421. Okay, 8.421. So this is how I would do this kind of by hand. Okay, this is how I would do this by hand. Okay, now this is my test statistic, is my chi-square test statistic. Okay, and it says, what's the p-value here? Or sorry, how do I get my p-value, right? So that's the test statistic. We want the p-value. Well, how many degrees of freedom do I have? Well, there are 6 categories. Okay, means 6 minus 1 or 5 degrees of freedom. Okay, so 5 degrees of freedom there. So the probability is chi-squared is greater than or equal to 8.42 with 5 degrees of freedom. Okay, the 5 degrees of freedom. So I would go to a calculator and I would calculate, okay, well, what is this for 5 degrees of freedom? Okay, so let's do that. Okay, so we want 8.42, right? And we want chi-squared is greater than or equal to 8.42 for 5 degrees of freedom. So let me pull up my calculator. Okay. Move this over. Okay, so calculator, where's my calculator? Calculator is in Santa Ana College, 219. Calculator, and I want Wabbit EMU. Okay, browser ROM for my computer, browse. Okay, I want that. Open, fish, and there's my calculator. No, I'm just kidding. There's my calculator. Oh, there's my tiny calculator. Okay, let's make that a little bit bigger. Come on, make it bigger. Let's make this bigger. Come on, you can do it. You can do it. Grow for me. Grow for me, bro. Let's see what happens when I minimize it and I maximize it. Oh, it's getting bigger. It's getting bigger. I can't do this. Get rid of this. Come on, bro. Grow. There we go. I knew you could do it. You could do it. No, it's not working. Okay, so let's just do this one over here. Stats. Okay, so we're going to go to actually second vars. Okay, so I'm going to go to down here. It says chi-square CDF. Okay, we did second vars, and it's chi-squared CDF. Okay, so I'm gonna do chi-squared CDF. And what's the lower? The lower is always 0. It's always 0 because it always starts from 0. What's the upper? The upper was, okay, I believe it was 8.42, right? Yeah, 8.42 or 8.42. The degrees of freedom was 5, and I paste that. Okay, so it's just going to be 0, 8.42, and 5. Okay, and it tells me that this is, okay, the probability, okay, is equal to, okay, for the CDF, is 0.8654. Where'd my pen go? Okay, so this is the probability that chi-squared is less than or equal to 8.42 is equal to, let's go back here, 0.8654. Okay, 0.8654. Okay, now there's a problem though, is that the probability is not what comes before it. The probability is what comes after it at 8.42, right? What is this cumulative distribution telling me? It's telling me it's all the stuff that comes before. So how do I get the stuff that comes after? Well, I reverse the inequality, but I subtract it from 1. So this is 1 minus the probability of x squared is less than or equal to 8.42. That's what this means. Okay, I want the complement. So this is 1 minus 0.8654, which ends up being 0.135. Okay, so that's how we get our p-value. Okay, 0.1, it says 0.135 here. Okay, so what's our conclusion? Well, since 0.135 is greater than 0.05, we fail to reject HO. What does that mean? That means that my expected amount is the same as my observed amount. Okay, my expected amount is the same as my observed amount. Okay, amount. So since, this is bigger than 0.05, we fail to reject HO. Okay, we don't reject, okay, we don't reject the null. We keep the null. Okay, which means that the expected and observed were close enough together that I had to agree that what the manufacturer said was true. Okay, that all 6 of those proportions, okay, all the 6 of those percentages for the M&Ms were what I was seeing in the back. Now, were they exact? No, but they were close. They were close enough. Okay, if they were farther away, right? If say I only end up with like 2, let's go back to they only end up with 2 red, right? That would be significant, right? That would be significant. But I'm 18, 26, 49. I'm off a little bit, but I'm under by a little bit. I'm over by a little bit, but it's okay. I don't have enough evidence to reject the claim. Okay. Okay, now let me see if I can go back to let's go to view, enable skin. Oh, what the heck? Why is this so dang small? Now it's huge. Boom. Okay. Calculator, view, enable skin. Let's see if we can move it. Can we move it now? Yay. Yes. Nice. Okay, perfect. Move that guy back. Okay, awesome. I don't want to lose this guy, so I'm going to pin him. I'm going to pin him to my taskbar if I can. Can I pin him? Maybe that's not allowed right now. Nope. Oh, there it is. Yay. Okay. Okay. So how would I do this if I just was given the amounts and I wanted to do it on the calculator? What if I wanted the calculator to calculate chi-squared for me? Well, the calculator will do that. You just have to set up 2 lists. One's going to be observed and one's going to be expected. Okay, so if I set up 2 lists here, if I go to stat on, okay, if I go to stat and then I go to edit, okay, and I just set up 2 lists. Okay, the first is going to be the observed, so 55, Okay, 20, 35, 49, 18, and 23. Okay, that's going to be my observed. What's my expected? My expected is 48, 28, 32, 40, 26, and 26. Okay, that's my expected, right? Observed and expected. Okay, so let's go to stat. Let's go over here to tests. Okay, I've set up my two lists, and I'm going to go all the way down to where I see chi-square goodness of fit test. Don't do chi-square test. That's different, but it's chi-squared GOF, goodness of fit test, and it's going to ask me a couple questions. What is your observed? Well, my observed was in L1. Okay. What is your expected? My expected was in L2. What is your degrees of freedom? It's 5. So this is already set up nicely. Okay, and I'm just going to calculate this, and it tells me what? It tells me, oh, look, my chi-squared was 8.42. Nice. And my p-value was 0.1345. 0.1345 or 0.135. Same p-value, same chi-squared. The calculator did it for us, which is awfully nice of it. Okay, and so we can just say, oh, we're going to fail to reject, which means all of these values here for the null hypothesis, all of these values are correct values. Okay. Okay. Okay, let's go on to the second application for chi-squared. The second application for chi-squared is we want to know what is the relationship between categorical variables here. Okay, categorical variables. Okay. In a clinical trial of effectiveness of echinacea for preventing colds, the results in the table were obtained below. Okay, we assume there is no association. We're trying to show there is a relationship. Okay, there's a treatment group, okay, and there's a placebo, there's echinacea 20%, and there's echinacea 60%. We want to know, okay, does echinacea help in preventing a cold or does it not? Okay, is there no real difference? Okay, so what is the hypothesis? Okay, the hypothesis is getting a cold is independent of treatment group. It means it's unrelated. That isn't related to the treatment group. Okay, what's the cold is dependent of the treatment group. Okay, so getting a cold is dependent of treatment group. Okay, that's my null. Okay, it's H1 or HA. Okay. Okay, the name of the test is the chi-square test for independence. Okay. Number 3, the requirements are the same as before. Okay, we just need to make sure that we have at least 5 observations. Okay, for each of these. Okay, and the calculations. Okay, so find the expected counts for a two-way table. This is called a two-way table because it has 2 ways to go. It's got rows and it's got columns. Okay, so it's a two-way table. Okay, it's got vertical and it's got horizontal. Okay. Okay, so we're going to use a chi-square calculator or a table to help us get the test statistic or the p-value on this one. Okay, and what are the degrees of freedom in this case? This is the number of rows minus 1 times the number of columns minus 1. So we don't have categories necessary. We have rows and we have columns. So we can see that we have, in this case, we have 2 rows, Okay, so in our example, we have 2 rows and we have 3 columns. So if I take 2 minus 1 times 3 minus 1, I will get degree of freedom 2. Why? Because 2 minus 1 is 1, and 3 minus 1 is 2, and 1 times 2 is 2. So 2 degrees of freedom. Okay. Okay, so how do we calculate the expected amounts, right? These are all of the observed amounts. Observed amounts. These are all the observed amounts. So how do I calculate the expected amounts? Well, here's what I do. So it's a little tricky. Okay, it's based on my observed amounts, but it's really based on my total amounts. Okay, so the number of people who got the placebo was 85 plus 15, which is 103. Okay, the number of people who got the echinacea 20% is 48 plus 14, which is 62. The number of people who got the 60% echinacea is 42 plus 10, which is 52. Okay. Okay, how many people got a cold altogether? Well, it's 178 if I add all that together. Okay, and then how many people did not get a cold? Well, the number of people that did not get a cold was 39 people. Okay, for a total of 270 people in the group. Okay, so now here's how I get my expected counts. Okay, is I take my row and I take my column and I multiply those two numbers together and divide by my total. Take the row number times the column number and divide by the total. And that's what we have over here. The expected counts are the row total times the column total over the grand total. Row total, column total over the grand total. Those are my expected values. Okay. So here's how this works. Is I'm going to do 103 times 178 over 217, and that will give me my expected amount. And I'm going to put that in parentheses here. All the expected amounts I'm going to have in parentheses. Okay. Okay. So I'm going to take 103 times 178, oops, 178, and divide that by the total 217. Okay, and I get about 84. And I'm gonna put them as whole numbers. I'm gonna round. Okay, these are just gonna be whole numbers. Okay, 84. Okay, what about this one here? This guy here. This is gonna be row total times column total. Sorry, row total times column total divided by total. So that's gonna be 62. Sorry, 62 times 178 divided by 217. And that's going to give me 51 as my expected amount. Okay, I'm going to keep doing this. This is going to be 52 times 178. I'm just going to kind of cheat and copy and paste this. Oops. Happened. Okay, let's arrow over. And I'm going to do 52 instead of 62 this time. And that gives me 43. Okay, so that's 43. Okay, now I'm going to do the bottom row. Instead of multiplying all of those values times 178, I'm going to multiply them by 39. So again, I'm going to kind of cheat. And I'm just going to borrow this. Okay, and instead of multiplying by 178, okay, I am going to multiply by 39. 30. Okay, and I get 19 for this one. Okay, if I did the same thing here, I would get 11 for that one. That's going to be 62 times 39 divided by 217.
Professor, how did you get the 103?
I added 88 and 15. Is that not 103?
Okay, thank you. No, I just wasn't sure. Thank you.
Yeah, these are all my row and column totals. Okay. Okay, 14 times 39 over 217. Okay, so I'm sorry, not 14. It's 62 times 39. Okay, 62 times 39 divided by 217. Okay, is 11. And then 52 times 39. I'll erase those. 52 times 39. Okay, 52 52 times 39 divided by 217, okay, is 9. So that becomes 9. And so this is going to be a chi-square again, based on the expected amounts and the observed amounts, right? So all of the ones in black are the observed values. All of the ones in, okay, all of the ones in red are expected. Okay, so again, I can do this. I can do this with observed and expected, and get my chi-square value, and then get my p-value. Okay, I'm gonna actually use the calculator to do this. Okay, instead of calculating it all by hand. Okay, I don't really want to do that. Okay, so I'm going to calculate all this. Now the problem is that I can't just list it out as rows. Okay, I have to do something called a matrix. Okay, I have to do something called a matrix, and that's where this gets kind of cheeky. Okay, is I have to hit the second X key, and I have to create a matrix, a 6x6 matrix for this. Okay, and so I have to go over and I hit second X to the -1 key, and I go over here and I say edit this, right? And I want what size matrix do I want? Well, I want it to have 2 rows and 3 columns. 2 rows and 3 columns. So 2 rows and 3 columns. And that allows me to put in the black numbers, which is what I want. I want to plug in the black numbers here, the observed. So this is 88. This is 48. This is 42. This is 15. This is 14. And this is 10. Okay? So I've plugged in this matrix A. Okay, and I'm going to hit second quit out of that. So once again, how did I hit matrix? I went to second, the X to the -1 key, and then I went over to edit, and I edited that matrix A. Okay, and if I do it again, okay, there's my matrix A, second quit. Now here's what we do. We're going to let the calculator do all the work for us, all the work. So we're going to go to stat, tests, and we're going to use that chi-squared test now. Chi-squared, not the goodness of fit one that we used before, because that was only when we had 2 rows or two columns. Okay, two rows. Okay, and we just had they weren't in. We were just wanting to know is the expected versus the observed. Here we have 6 expected and 6 observed, but they're not in order. Okay, they're not paired up. So we go to chi-square test, which is C this time. Chi-square test, and it says, hey, which matrix is your observed matrix? And it's matrix A. And then it asks me, which do you want your expected matrix to be? And I'm going to say, oh, I want the expected to be matrix B. And then they're going to say, oh, okay, just hit calculate. and I hit calculate, and it tells me, look, my chi-square is equal to 1.76. So chi-square was equal to 1.761. And what's my p-value? My p-value was 0.414, right? And what's my degrees of freedom? It even tells me my degrees of freedom is 2, which is what it should have been. It should have been 2. Okay, the degrees of freedom should be 2. Oh, okay. And the other way I can verify this is, remember, it asked me which matrix did it want me to have the expected amount, and that was matrix B. So you know what I'm going to do? I'm going to check that. I'm going to go to second matrix, and look, now it says that there's a matrix in matrix B, right? And I'm going to arrow down to matrix B, and I'm going to hit enter. And then and that brings up matrix B, and then I'm going to hit enter again. And lo and behold, look at this. This is all of the expected values that I already just calculated. It's 85 or 84, and then 18, right? Look at that, or 19, sorry, 84 and 19. What's over here? Well, that's 51 and 11 and 43 and 9. It already calculated all that for us. I didn't even have to calculate that. That was kind of nice to show you where it comes from, but I didn't have to calculate that. Okay, so what does this tell me? This tells me that since the p-value 0.4146 is greater than 0.05, we fail to reject HO. There is insufficient evidence to show that echinacea and getting a cold are dependent. Okay, so we can throw out the whole echinacea thing. Okay, so this is a controlled experiment, and we did a chi-square test to see if there was any difference in the expected amounts versus the observed amounts. And all we did was we needed to plug in that matrix, and it calculates the chi-square, right? Because this was and it was chi-square test was what we were looking at for this one. Okay.
Is there a same kind of test on StatCrunch?
Yeah, let me show you that chi-square test. Okay, so yeah, let me see where the chi-square test would be on StatCrunch.
Before you change it, can you scroll down a bit? I didn't get enough time to copy the verbiage.
Yeah, it's just failed to reject and insufficient. I mean, it's just basic. It's your basic conclusion. Okay. Okay, so this is a chi-square test. Yeah, let's see if we can find it in the goodness of fit is real easy to find in StatCrunch. I don't know if the chi-square test is there, but let's see. Let's see if we can find it. Okay, so where do I want to go? I want to get out of the calculator, and I want to get out of this thing. Okay, and I want to stop sharing. I want to minimize this so I can stop sharing this. Okay, so let's go to StatCrunch. Sign in. Okay, sign in. Okay, open StatCrunch. Okay, so yeah, let's see what we got here. So stats, okay, and there is goodness of fit. Okay, chi-square test. Goodness of fit chi-square test. That was for the other one that we did. Okay. Oh, my screen is blurry. I'm sorry. Let me see if I can share that again. Is that better? Yes, okay, perfect. Okay, so for the goodness of fit, let's do the M&Ms first to make sure that we know how to do the goodness of fit in here. So the M&Ms, okay, again, I can do the observed, which is 55, right? So 55, 20, 35, 49, 18, 23, okay, and then the expected I'm going to have in row 2, this is 48, 28, 32, 40, 26, and 26. Okay, so now let's do our goodness of fit real quick. Okay, so we can say, oh, goodness of fit chi-square test. It says which ones you're observed. Which ones you're observed. My observed is going to be variable 1, column 1. Okay, which one's my expected? My expected is variable 2. Okay, and then let's just compute this. Okay, and it tells me, look, my degrees of freedom was 5. My chi-square was 8.42, and my p-value, okay, my p-value was 0.135, okay, which is the same thing that we got before. Okay, cool, awesome. So now let's try the chi-square test. Okay, oops. Okay, so hopefully we could find the chi-square test in here. And if not, I'm going to Google it if I can't find it right away. Let's put in our echinaceas here. So for the placebo, it was 88 and 15. Okay. For the echinaceas, it was 48 and 14. And for the other echinacea, it was 42 and 10. Okay. So let's look at what we have here. So statistics, calculators, okay. So chi-square calculator. Let's see what this is. Nope, that's for the chi-squares. Distributions. Don't want that. Okay, so let's see what we got here. Okay, regression, goodness of fit. What's normality? Select columns. Test is Shapiro-Wilk. Do I want Shapiro-Wilk? Okay, select columns, variable 1, variable 2, variable 3. Variable 1. Okay, build, where, group by. Nope. Histogram with best fitting normal, save output in data table. Okay. What do I want to do here? This is independence, categorical independence. Group by where? I want to build that. Variable 1, variable 2, select the columns. Oh, can I select all of them? Shift. There we go. Shift to select all. Okay, so let me see what happens when I do this. Nope. Nope, that doesn't work. Goodness of fit results. It's still goodness of fit. I don't really want that. No, okay. So let's see what we can do here. What's a chi-squared test in StatCrunch? Chi-squared test StatCrunch. Stat. Okay, StatCrunch chi-square contingency table. What is this one? I'm gonna pull up. I just need the command. I know how to set it all up. I just need the command. What's the command?
In this example, we're going to look at
Okay,
how
this is
to
good.
deal
Working
with
columns
chi-square.
Okay, any day now.
Said, 6% of the males said
Come on,
human
come
activity.
on. I don't care. I want to see the table.
Data, doesn't matter what you call it here, it always just defaults if don't have anything, it's just variable 1. Then you have to have the actual frequency counts, right?
Yeah.
In other
Make it all
columns,
pretty.
and
I
it's
don't care
best to
about
have
making it all pretty. I want the command. What is the command?
select columns. That
There
means
we
select
go.
the columns that have the
Contingency
frequency
table. Contingency table. Select columns.
counts. So you have to select all 3 of these. You can do that by holding
Columns.
all the columns that have
You
the
want to care about
numbers
natural
in
problems?
them.
Oh, no. Okay.
Then down here, select
just
where
gonna
the
be-
row variables are, which
Okay. So let's go to contingency table here. Okay. So let's delete all this. Okay, so where's the contingency tables? So data. What you got here? Oh, I'm blurry again. Okay. Contingency table. Ah, here we go. Applets. Contingency table. Contingency table. Okay, let's see what we got here. Contingency table. Enter up to 5 comma delimited values. Row labels, column labels. I don't care about the labels. Okay. Oh, this is just to build it. I don't want to build it. I guess I gotta go back. Thought it would be easier than this. Stats. Stat tables, contingency with data. Okay, stat tables, contingency with data. Stat tables, there we go. Stat tables, contingency with data. There we go. Who knew? Okay, stat tables, contingency with data. Okay. Row variable. Okay, column variables. These are the columns. Shift. Oops. Shift. shift. Okay, so contingency table with data. What if I do this? Can I select these? No, I can't. Data, stats, tables, contingency with data. Select a variable. Expected count and control. Oh, variable one. Okay.
What you're probably gonna have to do is go to your columns and
Right.
enter that in row 1, and then your other column is gonna be vars 2. That way, you have to switch it off.
Right.
So you're gonna have to enter a row as a column.
Oh, enter a row as a column. Oh,
Yeah. And then that's why it's asking you what is your row, so that way you can pick the vars.
right. Okay. Okay, thanks. I'm going to delete these. Okay, so var2. Okay, let's try this again. So it really shouldn't matter though, like what's the row and what's the column. So I should have a 2x3, right? A 2x3 matrix. So let me do that guy again. So stack crunch.
In this video, you will learn to create contingency tables using StatCrunch. The data set I am using is called 2 categorical variables. This is just a toy data with data.
Okay, here we go. Okay, so I
I'll
see how they
select my
did
row
two-
variable as
they did
var1
two columns here.
and my column variable as var2.
Oh, row
and click compute.
Row 1. Right,
The resulting
row 1.
contingency table shows the individual unique values for each column in the first row and the first column of the table. The remaining cells show the frequency for each variable pairing, as well as the row-wise totals, column-wise totals, and the total number of pairs. The output also shows the results of a standard chi-square test for independence.
Okay,
Since the
First
cell
we get-
counts are
okay,
low
okay.
in this case, a warning message is displayed
Okay,
for these
let
test
me-
results.
okay, so let's see what Han suggests here. Okay, so Han suggests that I look at the chat. Come on, bring the chat up, bro. What the heck? There we go. Okay, you'll first need to enter the data with row and column labels. Okay, with row and column labels. Oh, okay. Okay, so let's do that. Placebo. Okay, select the columns for observed counts and select the column for the row variable. Click next. Click check expected count and select calculate. Okay. Okay, so set up the column, the rows and the, okay. So got a cold. Oops, let's turn caps lock off. Got a cold, okay, and did not get a cold. Okay, so did not get a cold. Oops, I gotta move these down. Control X. Okay. X, Control V, Control X, Control V. Okay, let's see what we got here. Got a cold, did not get a cold. Okay, and then placebo. Placebo, okay, and then 88, and then 19, okay, and then echinacea. What do you got here for me? Okay, the label should be var 1. The label should be var 1. The label should be where var 1 is var 2. What the hell does that mean? The label should be where var 1. Oh, the label should be var 1 is var 2. The label should be var 1. Oh, so I need to add a row? I need to add a column? Oh, okay, I get it now. Okay. Okay, now I get it. Okay, so this, what the heck? So this should not have a label? I'm so confused. Var 1 wants to have a label. It wants to have a label. Okay. Well, I'm just gonna go with var 2. And just know that I'm ahead by 1. Okay, so echinacea. How the hell do you spell echinacea? E-C-H-I-N, E-C-H-I-N, A-C-E-A, A-C-E-A, okay, and then 20%, right? Oh, screw it, I'm just gonna go 20% and 60, okay, boom, those are my labels. Except it's thinking that it's a X20 and X60. It's thinking it's a number. X60, okay. Ugh, in this one. Okay, so now I've got 48, 14. Okay, X60 is 42 and 10. 10. Okay, so now we're going to try to create a table, contingency table with data. Okay, so row, select variable. Okay, the row, select row variable. var 2, column variable. I don't get this. It's not working. Display row percent. I want chi-square test for independence. That's what I want. That's the first one. Confidence interval, gamma. Oh, it's got all these things. Okay, this is so confusing. Okay, so group by, I don't care about that. I don't care. var 2, right? And then select column variable. var 2 is the, okay, so 2, right? So delete row. I gotta watch the thing again. Okay, contingency table. C table. Crunch. Let's do it again. Okay, creating a contingency table. Okay, from raw data. Okay.
In this video, you will learn to create contingency tables. The data set I am using is called 2 categorical variables. This is 2 columns of data. The value B in 4 rows and the value of A in 6 rows. The var 2 column contains 10 values as well, the value of C in 6 rows, and the value of D in 4 rows. Let's begin by creating a contingency table of the data in the var1 column cross-classified with the data in the var2 column. To do so, under the Stat menu, choose Tables, Contingency, with Data. I'll select my row variable as var1 and my column variable as var2 and click Compute. The resulting contingency table shows the individual unique values for each column in the first row and the first column of the table. The remaining cells show the frequency for each variable pairing, as well as the row-wise totals, column-wise totals, and the total number of pairs. The output also shows the results of a standard chi-square test for independence. Since the cell counts are low in this case, a warning message is displayed for these test results. I'll discuss a better alternative for this data later in the video. StatCrunch 1/3, 33.3% are paired and click Compute. Options that can be added to the contingency table. For this example, I'll choose row percent and click Compute. Now the resulting table shows that 2/3, 66.6% of the A values are paired with the C values, and 1/3, 33.3%, are paired with the D values.
We already have our counts.
The table also shows a 50-50 split between C and D pairings for the B values.
I'll be with you in a second.
As mentioned prior, the chi-square test is not appropriate with this data due to the small cell counts. StatCrunch offers a number of different tests that can be computed from the contingency table output.
Okay,
Back
so
under
it's not data.
Options.
It's not data. It's summary. It's summary. That's the problem. It's summary data because we already have the counts for each of these. Okay, so is it still blurry?
Yes.
Still blurry. Okay, we stop the sharing. We go back to the sharing. Is it better? I guess better? No? Okay. I guess no one's complaining, so I guess it's better. Okay, so I already have the counts. I don't just have individual data. I have the counts already. So it would be a table, contingency table with summary. With summary. Okay. Select your columns. Okay. I want var2, var3, var4. Those are my columns. Okay. Row labels. Okay, row labels. Column labels. Okay, chi-square test. Let me just compute this, see what happens. You must select at least one value for row labels. Okay, so select row labels. R1. It's just not giving me whatever. Compute. What is it telling me? Got a cold is this. Those are the totals. Okay. Did I put them in correctly? Oh, no, I didn't. This should be 80. So this is that just gives me the totals. Okay, so placebo is 15. Oh, no, that's correct. Oh, I put in 19. That's the problem. This should be 15. Put it in wrong. Okay, that's correct. Okay, so that just gives me the counts. Okay, so we're getting closer here. Okay, so tables, contingency table with date, with summary, contingency table with summary. Okay, select columns, var 1 through var 4. Select variable, sure, compute. This gives me my counts. Holy Moses, that did it. We got it. Nice. Okay, that was exactly what the chi-square value should be. And that's exactly what the p-value should be. Okay, so let's go through that one last time. Okay, how did I get this table? Okay, well, I put in this guy here. Okay. And then I said, okay, var1 are my row labels. Okay. And then var2, var3, and var4, those are my columns. Okay. So var1 are my row labels. Those are the names of my rows. And var2, var3, var4 are my column data. And so I went to stats, tables, contingency with summary. And it says, select the columns for your data. And I did var2 through var4. And it says, okay, well, which column is your row labels? So that's the thing there. Which column is your row labels? And the column for my row labels was var1 column. Okay, and then it says, okay, well, what do we want? We want the chi-square test for independence. And then we hit compute, and it computed my values. Okay, so there you go. That's how you do it in StatCrunch. It's a nightmare, but we figured it out. Okay. Okay, let's move on from that. Woohoo. Okay. That's what you wrote. Okay, let's see. Let's go back to see what you wrote. Okay, so it says choose stat tables contingency with summary. Okay, perfect. So select the columns for the observed counts. Perfect. Select the column for the row variables. The problem is I didn't understand what that meant. Select the column for the row of variables. Like if you had said maybe row labels, select the column that contains the row labels. I don't know. Sometimes you just got to figure this stuff out for yourself. Click next and then check expected count. So yes, thank you very much, Han. You were correct. Thank you so much. At least you pointed me in the right direction. So I appreciate that. Okay, so again, you know what? This goes back to the whole thing of, I'm going to remember this now. Why? Because I struggled with it. You know what I'm saying? Like they say that a baby chick will die if it doesn't struggle to get out of its shell, because it becomes weak and frail. So the actual struggling to get out of its shell is what makes it able to survive after it is out of its shell. And so this kind of like goes back to the whole look. The struggle is important. When you're sitting there doing your homework and you're like, I don't know what to do here. I'm struggling through this. Sometimes that's very important. The struggle is what's going to make you remember. It's going to make you stronger in the end. So anyway, this is my 2 cents. So yeah, it's good. We're good. Thank you for everybody who contributed. Okay, so let's go back to the notes. Okay, let's go back to the screen sharing of the notes. Okay, let's get out of StatCrunch for now, sir. Boom. Okay. Chi-square test. Okay, and my calculadora. Okay, let's finish this up. We don't really have much left to do here. Okay, we have another example. Okay, example 3 records records of randomly selected bursts were obtained and categorized according to the day of the week they occurred. Based on the data from National Center of Health Statistics, because babies are unfamiliar with our schedule of weekdays, a reasonable claim is that bursts occur on different days with equal frequency. Okay. See the data that follows. Use a 0.01 significance level, okay, to test the claim. Okay. So, what type of test are we looking for here? What type of test are we looking for here? Well, we're looking for basically a goodness of fit test. Okay, why is that? Because we can test each of these values, okay, and find out what the expected value is for each of them. And here's how this works. Okay, so for this one, it's goodness of fit. Okay, so let's see how this works. So what is the null hypothesis? The null hypothesis is that all of the bursts are equal, okay, on all of the days. And so the probability that we have a birth on Sunday and Monday and Tuesday and Thursday, Friday, Saturday is going to be 1/7, right? 1/7. We would say that the probability of that would be all 1/7. Okay, and the null hypothesis is that it's not. At least one is different. At least one is different. Okay, at least one is different. Okay, requirements checked. Is it independent? Sure. Is it random? Sure. Is it large enough? Okay, is there a large enough sample? We have a pretty big sample there. Okay, so how many bursts do we have here? Well, if I add up all the bursts, the total number of bursts is 773. And if I were to take n times p, which is 773, and multiply by 1/7, that's my probability that all of them are the same, that equals 110, which is certainly bigger than 5. So each of those would be 110, about 110. The expected would be 110, 110, 110, 110, 110, 110, and 110. Does that make sense? All of them would be about 110. Okay, and if you really want to get, spicy about it, and you're like, well, how could that be 110? Well, it's because, and it's not 7, that would be 770 if it was exactly 110. You could add in the 0.4 if you really wanted to here. 110.4, 0.4, that's going to give you your extra 3. Okay, 0.4, 110.4, 0.4. Okay, but basically, that's your expected amount, right? 110.4. Okay, so that's the expected. So here I'm going to use a goodness of fit test. Okay, chi-square goodness of fit, because I just want to compare the number of bursts, the observed bursts, to the expected bursts, and we can easily calculate the expected for each of these days, right? Just think of it like the M&Ms. It's a blue or a red or a green or a yellow. So for this one, I'm going to go to my lists. Okay, I'm going to edit my lists. Clear. Okay. And clear. Okay, And so this is a chi-square goodness of fit test. So L1 is going to be my observed. Okay, so that's 77. That's 110. Oops, not 10, 110. Okay, and then 124. And then 122. And then 120. And then 123. And then 97. Okay, now I'm going to be a little sneaky in getting L2 because L2 is going to be, they're all going to be the same, right? So what I'm going to do is I'm going to say, oh, it's the total number divided by 7. Boom, look at that. And it calculates it for me. So the total number, 773, oops, 773 divided by 7. It'll be a much more accurate result this way. 773 divided by 7, 773 divided by 7, 773 divided by 7, 773 divided by 7, and 773 divided by 7. Boom. Whoops. Go to. What did I do wrong here? Okay, divided by 7. Okay. So now I have my observed and I have my expected. Now I'm going to go to chi-square goodness of fit. So I'm going to hit second vars. No, I'm not. I'm going to hit stats. And I'm going to go to tests. And I'm going to go to goodness of fit test. What the heck just happened there? Okay, let's keep going down. Okay, goodness of fit test. Boom, goodness of fit. And it says, what's your observed? My observed is L1. What's my expected? My expected is L2. What's my degrees of freedom here? My degrees of freedom is going to be the number of columns minus 1. So the number of columns, well, how many days in the week is there? Well, there's 7 days in the week. So 7 minus 1 is 6. 6 degrees of freedom. And then I'm going to calculate. And it says, oh, look, your chi-squared is equal to 16. Let's move this over here. 16.89 or 0.90895. I'll just do 895. And your p-value is really low. It's 0.009. Okay, so 0.009, 7, which is less than 0.01. That's a really low. I mean, we're pretty sure that they're not all getting born on the same day of the week. It looks like people like to take the weekends off of delivering babies. Kind of interesting. Okay, it's not there. It's, yeah, you know, they're kind of bunching up during the week. Okay, so looks like Tuesday through Friday, people are giving birth. Saturday, Sunday, Monday, not as many births. Okay, so what's our conclusion? So we did our calculations. Okay, that goes there. What's our conclusion? It says we're going to reject the null, that they're all the same. Okay, and we know that at least one is different. We're going to reject the null that they're all the same. You've been rejected. And we're going to accept the alternative. So there is sufficient evidence to suggest that the births do not occur with equal frequency throughout the week. Okay, so boom, there we go. Okay, let's do our last example. Okay, let's do our last example. This is a The last example is going to be a chi-square test because we're testing rights with left hand. Yes, no, male, female. Okay, we might even do this one in StatCrunch if I'm feeling spicy. Okay, so what's the null hypothesis? The null hypothesis is that gender and handedness are independent, but there's no correlation. So gender and handedness are independent. Okay, so gender and handedness are independent. What's my alternative? Well, that they're not, that they're dependent, that they're correlated. Gender and handedness are dependent. Okay, they're correlated. Okay, check the requirements. Check. Okay, is it independent? Yeah. Is it random? Yeah. Is there enough people in the study? Well, how many people were in the study? Well, if we add all these numbers up, we would get n is equal to 760. Okay, we get 760. Okay, and so all, okay, so that, yeah, all expected counts should be greater than 5. So all expected counts greater than 5, so we'll check that off. Now we want to do our calculations, okay? Now, again, if I do it on the calculator, okay, I just have to do one matrix, okay? So this matrix A is going to be a 2 by 2, 2 by 2, right? It's 2 by 2, not 2 by 3 anymore. So I'm going to go and edit this, and I'm going to edit it to a 2 by 2 this time. Okay, and I'm going to put in my observed values. Okay, 65 and 455. Okay, so now I'm going to do my chi-square test, right? Chi-square test. Okay, I did a 2 by 2 because we're doing a 2 by 2 this time. Okay, so the degrees of freedom on this one is 1, right? Because it's 2 minus 1 times 2 minus 1. 2 by 2 is a 2 minus 1, 2 minus 1, which is 1 times 1, which is 1. Degrees of freedom should be 1. Okay, so let's do, let's go to second. No, let's not. Let's just go to stats. And we're going to go to test. And I'm going to go chi-square test. Okay, just the chi-square test for independence. Observed is A. It's in matrix A. That's correct. Okay, hopefully I saved that okay. Okay, and then where do you want the expected to go? Matrix B. Calculate. Okay, and the chi-square here, which is correct for my calculations. Chi-square is equal to 1.364, and my p-value is 0.242, and I know that it did it correctly because the degrees of freedom it's showing me is 1. Okay, and then if I want to go back to matrix, okay, go back to matrix, the observed is matrix A. Okay, just making sure I plug that in correctly, and the expected would be matrix B. Matrix B, and those are my expected counts. So if they wanted you to do the expected counts. Now, what does this big p-value tell me? This big p-value is bigger than anything that I would compare it against. It says use 5% significance level. So I'm going to compare that against the 5% significance level. And what is the conclusion? The conclusion is that there is insufficient evidence. To reject the null. Therefore, handedness and gender appear to be independent. Boom. And that's it. Okay, now, should we do this? Should we try this one on StatCrunch? Should we be so bold? I don't know. Well, we'll be so bold, and then I'm gonna stop. I'm gonna leave after this. Okay, so let me do the StatCrunch real quick. Okay, so hopefully you can see my screen. Okay. Okay, so let me share my screen. Somebody just come in because your microphone's on. Turn everybody off. Everybody's in. Nope. Boom. There you go. Okay. Okay, so open StatCrunch. Okay, let's see what's going on here. Okay, so I gotta do my labels. Let's do our labels real quick. Okay, label is male. Okay, female. Okay, var1 is yes. I'm left-handed. I'll just say, you know, instead of yes and no, I'm gonna go left. Okay, and right. Okay, left-handed versus right-handed. Okay, so those are left yes, left no. Okay, it's fine. Okay, so left is 23 for the males and 65 for the females. Okay, right is 217 for the males and 455 for the females. And so I want to go to stat, tables, contingency table with summary. Okay, select var1 and var3. Okay, select my var1 as my rows and compute. Let's see what we got here. Okay, so does that give me the same amount as I got before? Yes, it does. Hallelujah. Praise the Lord. And that's it. And I am done. I am ready for some Cinco de Mayo margaritas or something like that. I don't know about you. Okay.
You don't drink.
What? I don't drink actually. So, but you can have virgin margaritas, right?
It's not
You don't have to have tequila in
like
there.
having O'Doul's. O'Doul's isn't the same.
You could just have a blended lime frozen lemonade, basically. Right? It's allowed, I think. Sounds good. Sounds good. Okay, I'm good. I'm good if you guys are. I'm not going to stick around to do homework. That was kind of a long lecture. So I'm ready to it's a holiday. I'm sorry, it's a holiday. I'm gonna call a holiday and we're done. So I'll see you guys mañana. No. Mañana, whatever that means. So no homework? No, you got homework. Okay. It's not due until next Tuesday. Okay. So you don't have to do it tonight. You can do it tomorrow because tomorrow is not a holiday. Okay. Okay. See you guys later. Bye. Hasta la pasta. Something like that. Oh, does it say it's due on 5/7? I'll change that. I'll change that then. Thank you. Thank you. Yeah. It's all good. We'll make it due on 5/12. Okay. Well, which homework? Which homework are you talking about? The homework for chapter 11 or the homework for chapter 10? I'm gonna have to take a look at that. Okay, because chapter 11's homework is not due for a long time. Okay, okay, sounds good. Sounds good. Okay. Okay. Okay, I'll see you guys later. Bye.